So before I get too far ahead of myself, let's go ahead and compute an example of a vector line integral. So this asks me to compute this. This whole notation is asking me to compute the vector line integral. I don't want this notation to be confusing. It's sort of a generic way of saying the vector line integral. And we're given our vector function. It's x squared for the first component and then negative xy for the second component. We're also given the path that we want to compute this over. It's the path cosine t sine t as t goes from 0 to 2 pi. And recall, we just talked about the formula. So in this case, t is going from 0 to, not 2 pi, sorry, pi over 2. And I need to know what is f of c of t. And then I'm going to dot that with c prime of t dt. And once I compute what each of these pieces are, then I can do my integration. So piece by piece, first, let's look at what is f of c of t. F of c of t, I'm going to plug in the fact that c of t is given by this function, so that means that my x components are equal to the cosine of t, and my y components are equal to the sine of t. So I'm using my path function to tell me what my f evaluated at this c of t is going to be. So in this case, f of c of t is equal to my x component squared, which is in this case the cosine of t squared, and then my y component is going to be negative cosine t sine t. That's my f of c of t chunk. I also need to compute what is c prime of t. C prime of t in this case is the derivative of my c of t function. The derivative of cosine is negative sine of t. The derivative of sine is cosine of t. And those are the two pieces that I need. Notice that I sort of flip-flop notation. Here when I'm describing this path, I'm describing it as points in space. Whereas down here, when I describe the derivative, I describe the derivative as a set of vectors. Sometimes I'm a little sloppy going back and forth between these notations, essentially because they're two representations of the same thing, whether they're the tips of vectors or points in space. Either way, I'm going to erase some of this scratch work. And we'll see that this integral is going to be the integral from t equals 0 to pi over 2 of this vector dotted with this vector. So it's the vector cosine squared of t, comma, negative cosine t sine t, dotted with the vector negative sine t, cosine t, dt. Recall that for dot products, it's the first term multiplied by one another plus the second terms multiplied by one another. So this integral ends up being the integral from t equals 0 to pi over 2. I'm going to take this x term and multiply it by this y term, and I end up with negative cosine squared t sine t. And then I'm going to add this term multiplied by this term, which ends up being negative cosine squared t sine t dt. So when I subtract these two, I end up with negative 2 cosine squared t sine t dt, correct? Because I have the same term twice. And notice, this is where we can be a little tricky. I know that the derivative of cosine is negative sine, so I'm going to have to do a u substitution. My u substitution in this case, I'm going to let u equal the cosine of t, because that way my du is going to be equal to negative sine of t dt. And so negative sine of t is taken care of by this negative sine and this chunk and the dt. All of these pieces turn into my du, and so I end up with just 2u squared du. I'm going to integrate with respect to u, and I end up with 2/3 u cubed. And rather than reevaluating the bounds, I'm going to change back my variable. U, recall, was the cosine of t, so I get 2/3 the cosine of t cubed, all evaluated from t equals 0 to pi over 2. The cosine of pi over 2 is 0. And the cosine of 0 is 1. So I end up with negative 2/3. And that's my final answer, negative 2/3. One thing that I want to point out is that in this case our answer was negative. Does that make sense? Sure, it makes sense. It just means that the work that was done as I traveled along this path by this vector integral, by this vector value function, the line integral has a negative value, so I'm going against the flow. Let's take a quick look geometrically. So this is a function. The vector field is something that we can explore in greater detail using technology. But if you look at this, you can see that I plotted a couple of the vector field outputs in the blue arrows right here. And we see that because my y component is given by negative xy, and here when I'm in the first quadrant, both x and y are positive, it means that my y's are pointing down. Whereas my x components are squared, so they're always moving positively. So it makes sense that as I travel along this arc in this direction, my work is going against me. So it makes sense geometrically that we got this negative value. So I want to conclude, I want to conclude by laying side by side everything that we've talked about. So we talked about scalar line integrals and we talked about vector line integrals. Recall when we were talking about scalar line integrals, they're called scalars because the outputs of our function are scalars. They're real valued outputs. That's why we have a little f. Whereas over here with vector line integrals, we have a capital F signifying the fact that the outputs of these functions are vectors. Similarly, when we look at the formulas for these, when I compute the line integral for a scalar value, scalar function, we get the formula that it's going from t equals a to b, our change in time over this path c, is f of c of t times the magnitude of the derivative of c of t dt. And notice this correspondence again, that here, when we write it sort of generically, we're taking with respect to the lengths, but because lengths don't necessarily correspond to equal chunks in time, we need to make sure that we multiply by the speed. So this part down here is telling us how far have we traveled along the path, and this is telling us the height of the path. And that gets me to my final point, that this scalar line integral is measuring an area, if you wanted to visualize it as area, where the length of the path is the base, and the height of the function is given by the height. And those two things multiplied together, but they have to be multiplied together at incremental values of t, because the height of that path is going to change for different values of t. Compare that over here to with our vector line integrals. We're also computing f of c of t, but rather than multiplying by the magnitude of c prime of t, we're instead taking the dot product with the derivative of t. And this comes from the fact that we want to make sure that we're measuring the amount of work that's in the same direction as our motion. So one way to visualize this is to think of this as the sum of all of the forces that are exactly in the direction of the path that I'm traveling. And so if I'm traveling against my vector field, then I'm going to get negative values for this. Similarly, if my function here is below the xy plane, then I would get negative values for this integral because those areas are below the xy plane. So hopefully this is a nice summary of everything that we've done. There are a couple of properties of scalar line integrals and vector line integrals that we didn't talk about, and I'm going to write them down now and highlight the fact that these are important things for you to know that you'll explore in greater detail in your homework. So one thing is the fact that scalar line integrals are independent of path. shouldn't say that. They're independent of path parameterization. Meaning that, let's say that I have exactly the same physical path. I'm tracing out exactly the same length along the bottom, but I'm going at a different speed. You'll still get the same line integral, and that makes sense because it's consistent with the geometry. So I could have two paths that sort of looked different algebraically. If they actually trace out the same path, then you're going to get the same line integral. Over here, our vector line integrals are also independent of path parameterization, but they must go in the correct direction. So if you have the same path, but if I'm going the opposite way, then I'll get a negative value. And if I go in the other direction, I would get a positive value. So they're independent of path up to a sign change, up to whether they're positive or negatives of one another. And that's something that you'll explore in your problem set. Thanks so much. That's it.